There is a smudge of light in one of the James Webb Space Telescope's images that should not be there. It is small. If you saw the full frame, your eye would slide right past it, because next to the bright foreground stars and the swirls of nearer galaxies, this thing is barely a few faint pixels of deep red. It does not glow. It does not announce itself. It is the kind of object you would only notice if someone circled it for you and told you to look again. And yet the astronomers who study the early universe will tell you that this quiet little point of light is one of the most unsettling objects ever recorded. Not because of what it looks like, but because of when it comes from. The light from that smudge left its source more than 13 billion years ago. It has been travelling, unbroken, through expanding space for almost the entire history of the universe. When that light began its journey, there was no Earth. There was no sun. There were no heavy elements to build a planet from. No rock. No water. Nothing that would later become you. The universe was a few 100 million years old, fresh out of its first darkness, and it was supposed to be nearly empty of the kind of object Webb is staring at. The faint red light should have come from almost nothing, because almost nothing was supposed to be there yet. Instead, Webb keeps finding galaxies in that ancient light. Bright ones, big ones, galaxies that look settled and grown when, by every careful model we have, they should still be scattered seeds barely beginning to gather. And the way people describe them online has hardened into a single dramatic phrase, repeated until it sounds like fact. Galaxies that are too old to exist. That phrase is wrong, and that is exactly why it is worth your next several minutes, because the truth underneath the headline is stranger than the headline, and quieter, and much harder to shake once you actually understand it. Nothing in these images is older than the universe. Nothing can be, and the same measurement that reveals these galaxies is the thing that proves it. But something about how fast they grew, how brightly they burn, and how many of them keep turning up, refuses to fit the story we thought we had already finished writing. And if you like the kind of space story where the mystery comes from real physics rather than from someone shouting at you, this is exactly the kind of question worth sitting with carefully. So stay close, because to feel why a faint red dot can keep professional cosmologists awake at night, you first have to understand what its colour is actually telling you, and why a telescope had to be built to see a colour that human eyes cannot. It helps to remember what this telescope cost us, in time and in nerve, before it ever returned a single image. Webb was decades in the making, and billions of dollars in the building, and for years it was the most expensive scientific gamble in the sky. Folded up like a piece of origami and flung 1.5 million kilometers from Earth to a spot where a single serious mistake could not be repaired by any human hand. The whole point of that gamble, the reason it was judged worth the risk, was to catch exactly this kind of light, the faint, stretched, infrared glow of the universe's first galaxies, the chapter that no telescope before it could ever reach. The people who built it fully expected to be rewarded with the dim, the small, and the rare. They were rewarded instead with the bright, the early, and the strangely abundant, which is a very different prize, and a far more unsettling one. And the stakes here are not abstract, even though the distances certainly are. When we ask how the first galaxies formed, we are really asking the first question in a chain that eventually runs all the way to us. Those early galaxies are where the first heavy elements were forged, the carbon and oxygen and iron that would much later become planets, oceans, and living bodies. If we have the timing of that very first step badly wrong, then we have something wrong about the opening of the story that ends with you sitting here, watching ancient light glow on a screen. That is why a faint red smudge can carry so much weight. It is not just a distant object catalogued in a survey. It is a clue about where everything, ourselves included, actually came from, and a quiet hint that we may have misjudged how the opening pages were written. Here is the part that hooks the people who do this for a living, the part the headline never gets to. This is not one galaxy. It is not a single freak result that one careful measurement could quietly erase. Webb has now found a whole growing list of these too early, too bright objects. And each time astronomers push deeper into the data, they do not find fewer of them. They find more. The frontier of the most distant known galaxy keeps moving outward, toward the very beginning. And the same problem keeps waiting there when they arrive. Every record that falls reveals another object that is brighter and more developed than it has any right to be. So the real question is not whether one smudge is genuine. Confirmed galaxies have settled that. The real question is why the early universe, again and again, in survey after survey, looks busier, brighter, and more grown up than our best theory said it had any right to be in its first few 100 million years. To answer that honestly, we have to do the thing the headline skips entirely. We have to slow down, walk the evidence one careful step at a time, separate what is measured from what is guessed, and watch for the exact moment where a simple, solid measurement turns into a problem that will not close. It begins with color. In the distant universe, it always begins with color. Because out there, color is not decoration. It is a clock, a ruler, and a warning all at once. Everything that follows is really just the patient work of reading that one signal as carefully as it deserves. And the deeper we read it, the clearer it becomes that the early universe is sending us a message our best theory did not expect to receive. To understand why that faint red smudge is frightening, you have to understand what its redness is hiding. Because in the distant universe, the color of a galaxy tells you how long its light has been traveling, and therefore, how far back in time you are looking. Start with something ordinary and familiar. When a fire engine races past you, the pitch of its siren drops as it moves away. The sound waves get stretched by the motion, and the stretching is something you can hear with your own ears. Light does the same thing, but instead of pitch, what changes is color. When a source of light moves away from you fast enough, its light gets stretched toward the red end of the spectrum. Stretch it far enough, and visible light slides out of view entirely. Past red, into the infrared. The kind of light your eyes cannot see at all, but a telescope can be built to catch. Now here is the strange part that makes this entire field possible, and it is worth getting right, because almost every confused version of this story gets it wrong here. The galaxies we are talking about are not simply flying away from us through space the way the fire engine drives down the street. Space itself is expanding, everywhere, all at once. And as it expands, it carries the light inside it along for the ride, stretching that light over its whole journey. The longer the light has been traveling, the more space has expanded around it, and the more its color has been dragged toward the red. Astronomers measure that total stretch with a single number, and they call it redshift. The bigger the redshift, the more the light has been stretched, the longer it has been on its journey, and the deeper into the past you are looking. A galaxy with a small redshift is a near neighbor, seen as it was not so long ago. A galaxy with a huge redshift is something else entirely. Its light is old. Its image is old. You are not seeing that galaxy as it is now. You are seeing a single moment that ended billions of years ago, preserved only because the light has been crossing space ever since and has not finished arriving until now. This is the first idea to hold on to, because it quietly rewrites how you read every image that follows. When Webb captures one of these record-breaking galaxies, it is not looking through a clean window at the early universe. It is catching a message that was sent across nearly the entire age of the cosmos and is only landing on its mirror today. The galaxy that sent it may have changed beyond recognition. It may have merged into something far larger. It may, in a real sense, no longer exist in anything like the form we see. The light is all that is left of that moment, and the light is the only thing we get to measure. So when researchers say a galaxy sits at a redshift of around 14, they are making a precise and checkable claim. They are saying its light has been stretched to more than 15 times its original wavelength. They are saying it has been crossing space for more than 13.5 billion years. And they are saying we are seeing it as it was when the universe was only a few 100 million years old, roughly the first 2% of all cosmic time. The very first sliver. To put that in human terms, if you compressed the whole history of the universe into a single year, these galaxies would be light from the first few days of January, and everything you have ever known would happen in the last hours of December. There is one more twist that makes this even harder to hold in your head, and it is entirely real. Because space has kept expanding the whole time the light was travelling, the galaxy that emitted it is now far more distant than the distance its light has crossed. The light has travelled around 13.5 billion years to reach us, but the galaxy itself, dragged outward by the ongoing expansion of space, now sits tens of billions of light years away, far beyond anything we could ever signal or reach. It is receding so fast, carried by expanding space, that no message we could ever send would catch it. It is worth pausing on what the universe was actually like at the moment that light set out, because it was not a smaller version of today. It was a fundamentally different place. Everything was packed far closer together, since all the matter now spread across billions of light years was crammed into a fraction of that volume. The afterglow of the Big Bang, which today is a faint, cold whisper, was then a warm bath of radiation filling all of space. The cosmos was younger, denser, hotter, and far more crowded. And that crowding matters for the mystery to come. Because gas that is packed tightly together can cool and collapse and form stars more readily than gas that is thinly spread. The early universe was a pressure cooker compared to the calm, dilute cosmos we live in now, and any honest account of how fast it could build galaxies has to start from that difference, rather than from the gentle conditions around us today. And that is where the trouble truly begins. Because in that thin opening sliver of cosmic time, the rules of galaxy formation say things should be small, faint, simple, and rare. The first stars should only just be switching on. Galaxies should be little knots of gas, dim and unsettled, slowly gathering themselves together. The redshift tells us, with confidence, that we are looking at exactly this beginning. The brightness of what we find there tells us something at that beginning is already far further along than it should be. Those two facts are not supposed to share an image. The distance is solid. The interpretation of what that distance implies is where the entire mystery hides. And to see it clearly, you have to understand how Webb catches this light at all. When every telescope before it went blind trying. That blindness was not a flaw in those telescopes. It was a boundary in the light itself, and crossing it required building something designed from the ground up to see in the dark colours that expansion leaves behind. That is the machine that finally pulled these galaxies out of the darkness, and the moment it did, the trouble started in earnest. For decades, this corner of the universe was simply out of reach, and the reason for that is almost cruelly elegant. The very stretching that makes these galaxies ancient is also exactly what made them invisible to everything we built before Webb. Think about what redshift does to light over 13 billion years. A young galaxy in the early universe pours out most of its energy as ultraviolet light, the high-energy glow of hot, newborn stars packed close together. But by the time that light reaches us, the expansion of space has stretched it far past the visible colours, past the deepest red your eye can register, and deep into the infrared. To us, the brightest early galaxies are not blue or white the way they were when they shone. They have been reddened all the way into heat. Faint, cold-looking infrared, the kind of signal that hides in exactly the same range where any warm object, including a telescope's own structure, quietly glows. The Hubble Space Telescope, for everything it gave us, could only reach so far into the infrared, capturing wavelengths up to roughly a micrometer and a half. With that reach, it caught the early universe's toddlers, galaxies from around 1 billion years after the beginning, and even those it caught straining at the very edge of its ability. Beyond that edge, the most distant galaxies had slipped entirely out of the colours Hubble could detect. They were not too small for Hubble to see, they were the wrong colour for it. Their light had been pulled past the end of Hubble's vision, into a band it was never built to read. Webb was designed specifically to chase that vanished light. It is, at heart, an enormous infrared eye. Its main mirror spans more than 6 meters, far larger than Hubble's, which means it gathers many more of these scarce, stretched photons. It can detect wavelengths far into the infrared, reaching the bands where 13 billion years of cosmic expansion deposits the light of the first galaxies. To do that without being blinded by its own warmth, Webb sits about 1.5 million kilometers from Earth, shielded from the sun by a sunshade the size of a tennis court, chilled to a few tens of degrees above absolute zero. It is, in effect, a frozen telescope parked in the dark, built to see the exact part of the universe that redshift had been hiding from every instrument before it. When it opened that eye, it did something deceptively simple. It took long, deep exposures of small patches of sky, the way you might leave a camera shutter open in a dark room to collect every faint scrap of light over many minutes. In those patches, objects that were completely absent from Hubble's images of the very same spot began to appear. Faint red points, glowing only in the longest wavelengths, present in Webb's data and simply not there in the older pictures. That absence is itself a powerful clue. If something shows up only in the reddest, most stretched filters and vanishes entirely in everything shorter, its colour is shouting that it is extremely far away. Astronomers call this the dropout signature, because the galaxy drops out of the bluer images, but a faint red dot in an image is not yet a confirmed distance. And this is where the science has to become careful, because the difference between two methods is the difference between a rumour and a fact. The first method is photometry. You measure how bright the object is through several different filters, each one letting in a different band of light, and from the pattern of brightnesses, you estimate the redshift. It is fast. It lets astronomers scan thousands of objects at once and flag the promising ones. But it is an estimate, and estimates can be fooled. A dusty, ordinary galaxy much closer to us can sometimes wear colours that mimic an extremely distant one, because dust also reddens light. A photometric redshift is a strong suspicion, not a verdict. The second method is spectroscopy, and it is the one that turns suspicion into proof. Instead of just measuring brightness through a few broad filters, Webb spreads the object's light out into a full spectrum, like a prism splitting sunlight into a rainbow of fine detail. In that spread-out light, specific features appear at specific wavelengths. The most important is a sharp cliff in the spectrum, a place where the light suddenly drops to almost nothing because clouds of hydrogen gas in and around the galaxy absorb everything beyond a certain wavelength. The exact position of that cliff is a fingerprint of distance. If it sits precisely where a redshift of 14 would place it, the galaxy is genuinely at a redshift of 14, and there is very little room left to argue. In practice, these two methods work together as a kind of relay, and understanding the handoff makes the discoveries feel less like luck and more like a hunt. Webb's wide-view infrared camera sweeps a patch of sky and captures everything in it at once, producing the deep images where faint red dropouts first reveal themselves as candidates. That camera is fast and efficient, but it can only estimate distances, so once the most promising candidates are flagged, astronomers point Webb's spectrograph at them, one by one, and let it spend hours gathering enough of their feeble light to spread into a full spectrum. The camera casts the net. The spectrograph identifies the catch. This is why the early, dramatic numbers and the later, sober confirmations often came months apart, and from different stages of the same process. The exciting candidate arrives quickly. The verdict takes patience, and a great deal of precious telescope time, which is why only a fraction of the most interesting candidates have been fully confirmed so far. This distinction matters enormously for everything that follows, because the loudest versions of this story blur it completely. A photometric candidate is exciting but uncertain, and several early ones did not survive. A spectroscopically confirmed galaxy is locked in. The objects that truly broke the calm of the field, the ones that turned a surprise into a problem nobody could dismiss, are the ones that survived this second, harder test. And the first of them arrived far sooner than anyone was ready for. In the telescope's very first season of looking at the sky, what it found there did not wait politely for astronomers to settle in and calibrate their expectations. It arrived almost immediately, in the very first batch of deep data, and from the start, it looked wrong in a way that was hard to explain away. When Webb's first deep images came back in the summer of 2022, the astronomers who had waited decades for this telescope fully expected to be surprised. They were not expecting to be unsettled within the first few weeks of looking, and certainly not by results so strong that papers were being rushed out almost as fast as the data could be analysed. The plan, roughly, was this. Webb would push back into the early universe and find the faint, small, unfinished beginnings of galaxies, and by carefully studying how dim and how rare they were, astronomers could trace the slow climb from near nothing toward the grand spiral and elliptical structures we see today. The early universe, the thinking went, should be a thin gruel, a few small clumps of stars scattered here and there. The brightest, most massive galaxies should be vanishingly rare that far back, because there simply had not been enough time for gravity to gather that much material together and for stars to form in such overwhelming numbers. Instead, the early images held galaxies that looked too bright, too massive, and too mature to belong where they were found. Not subtly, not safely within the comfortable margin of error, object after object that, on first analysis, seemed to contain far more stars, far more assembled mass than the available time should have allowed. The reaction in the field was a mix of delight and disbelief. Some of the candidates were so unexpected that researchers half joked they might be illusions, results so strange they could collapse the moment someone looked harder. The honest description was that the early universe, in Webb's first glimpse, simply looked wrong, too far along for its age. It is worth remembering how fast this all happened. because the speed of the surprise was part of its force. Webb's first full-color deep image was unveiled to the public in the summer of 2022. A single tiny patch of sky crowded with thousands of galaxies, some of them smeared and magnified by the gravity of closer galaxy clusters. Within days and weeks, teams running dedicated survey programs began combing through fresh data of seemingly blank patches of sky, and candidate galaxies at startlingly high redshifts began tumbling out almost faster than anyone could properly vet them. Some of those first candidates were so extreme that researchers openly hedged their bets, describing them as objects that might be record-breaking ancient galaxies or might dissolve into something ordinary once a spectrum was finally taken. That caution was wise, because a number of those very first candidates did shift or soften later on. But the broader impression they created of an early universe stocked with far more bright galaxies than anyone had expected did not soften. It only sharpened as the better data arrived. To feel the weight of this, you have to understand what maturity actually means for a galaxy. Because it is not one quality, but several stacked together. A truly young galaxy should be a chaotic, gas-rich, irregular thing. Its light should be dominated by hot, new stars, and its chemistry should be simple, made almost entirely of the hydrogen and helium left over from the beginning, with very few of the heavier elements that only get forged inside generations of stars and scattered into space when those stars die. Maturity shows up as more mass, more concentrated structure, and a richer chemical fingerprint, the unmistakable signature of stars that have already lived, died, and seeded the next generation. Every one of those things is supposed to take time. They are supposed to take more time than the early universe had yet spent. And yet the signatures kept appearing too early, in object after object, galaxies far brighter than the models predicted for their age, hints of heavier elements where there should have been almost none. Compact, dense concentrations of stars in an era when material was supposed to still be loosely and thinly spread. Each of these on its own might be explained away by some special circumstance. Together, repeating across many independent objects, they formed a pattern, and the pattern pointed in a single uncomfortable direction. The first galaxies seem to have assembled themselves faster than our entire theory of galaxy formation said was possible. It is worth being precise about what the problem is and what it is not, because this is exactly the point where the popular version flies off the rails into nonsense. The problem is not that these galaxies break the laws of physics. Gravity still works, light still travels at the same speed it always has. The problem is narrower, and in a way far more interesting. Our standard picture of how galaxies are built rests on a chain of steps that each take a certain amount of time. Gas has to cool and fall together. Stars have to ignite. Enough of them have to form, and enough of them have to die and enrich their surroundings to make a galaxy bright and chemically mature. To build something massive and luminous and enriched, you normally need that whole chain to run for a long while. The early Webb galaxies looked as if the chain had somehow sprinted to a late stage, while the cosmic clock still read almost the very beginning. That is the true shape of the surprise. Not impossible objects, but an impossible-looking schedule. A universe that, in its first few 100 million years, was already producing the kind of bright, substantial, chemically enriched galaxies we expected to take much longer to appear. The light said early. The galaxies looked late. And nothing about the basic measurement of distance, once it was confirmed with the spectrum, made that contradiction go away. This is the moment a careful surprise hardened into a genuine mystery. Up to here, you could still imagine the data was simply being misread, that the distances were wrong, that these were nearby imposters dressed in distant colours. But as confirmations came in and the redshifts held firm under spectroscopy, that escape route narrowed and then closed. The galaxies were as far away as they looked. They were as early as the light claimed, and they were still, stubbornly, too grown up for the time on the clock. Which is precisely where the story began to mutate in the retelling into something far more dramatic, far more viral, and far less true than what the scientists had actually found. And once a true thing gets retold as a more exciting false thing, the false version almost always travels faster and further than the careful one. That is precisely why the correction is worth making slowly, before going any further into the evidence. Somewhere between the careful scientific papers and the headlines that spread across the internet, the story changed its shape. And the version most people ended up hearing is the one we now have to take apart, piece by piece. Because the gap between it and reality is the whole point. The popular phrasing is that Webb found galaxies older than the universe, galaxies too old to exist, galaxies that quietly prove the Big Bang never happened at all. It spreads because it is thrilling and simple, and because it flatters a particular instinct, the satisfying wish that the experts had it all wrong and that a single image could overturn everything they ever told us. But it is not what the data says. And the gap between the headline and the science is not some minor technicality to wave away. It is the difference between a real problem and a fake one, between a mystery you can investigate and a slogan that ends the conversation. Start with the plainest correction of all. Nothing Webb sees is older than the universe. Because out here, age and distance are the same coin viewed from two sides. When astronomers say a galaxy is at a redshift of 14, they are saying its light is young in one sense and old in another. It left its source when the universe was only a few 100 million years old, and it has been travelling ever since. That galaxy formed inside the cosmos and cannot possibly be older than the cosmos that made it. The phrase, too old to exist, smuggles in a contradiction that the measurement itself flatly rules out. These galaxies are not ancient relics that somehow outlived time. They are early arrivals, caught at their own birth, and the light is the proof of exactly that. To see just how self-defeating the headline is, follow its own logic for a moment. The only reason we know these galaxies are distant at all is the redshift, the stretch in their light. But that same stretch is what tells us they are early, seen close to the beginning. The measurement that makes them far away is the identical measurement that makes them young in cosmic terms. You cannot keep the distance while throwing away the youth, because they are the same number, wearing two different names. To claim a galaxy older than the universe, you would have to accept the redshift and reject what the redshift means in the same breath, which is not a discovery. It is a contradiction with a dramatic costume on. This is also why the pattern keeps repeating with Webb. Every time the telescope sets a new distance record, the same misleading phrase resurfaces, recycled almost word for word, even though the underlying science has never once supported it. The headline is not tracking the data. It is tracking our appetite for the data to mean something it does not. So what is actually too much? If not the age, the maturity, the brightness, the pace of assembly, the number of them. The honest sentence is clumsier than the headline, but it is the true one. Webb keeps finding galaxies that are too developed for how early we are seeing them, too bright for their epoch, too massive for the time available, too rich, in some cases, with the heavy elements that take whole generations of stars to make. The shock is not that the clock is broken. The clock is fine. The shock is that the building got finished suspiciously fast. And this correction is not a downgrade of the mystery. It sharpens it into something far more dangerous to a theory. galaxies older than the universe is a paradox with no exit. The kind of claim that, if it were ever true, would mean every measurement we trust is wrong at its very root. That is not a mystery you can investigate. It is just a wall you bounce off. Galaxies that grew too fast is something completely different. It is a problem with edges. It is a problem you can poke at from many directions, a problem that points directly at specific missing pieces in our understanding of how the first stars and galaxies actually came together. One version slams the door, the other one opens it and shows you a hallway. It matters for another reason too, one that goes beyond this single story. The false version quietly poisons the way people think about science itself. If you believe Webb disproved the Big Bang, then you also have to believe that thousands of professional astronomers either failed to notice the most important discovery of their lives, or noticed it and chose to hide it. You have to believe that a confident phrase on a screen knows more than the entire careful spectroscopic record built by people who have devoted their careers to exactly this question. Neither of those is remotely true, and the proof is in who is raising the alarm. Because here is the part the conspiracy framing cannot survive. The same researchers who found these galaxies are the very ones loudly pointing at the problem. They are not quietly defending a crumbling theory and hoping nobody notices. They are highlighting the crack themselves in their own published papers, in their own interviews, and asking openly what it means. That is precisely what the scientific process looks like when it is working as intended, not when it is collapsing. A field that was hiding a failure would not keep publishing the failure on the front page of its own journals. So we can set the headline down now, gently, and keep only the part of it that was ever real. There is a genuine tension in this data. It is not about age, and it is not a disproven universe. It is about speed and brightness and sheer abundance in the first sliver of cosmic time. And the moment you accept that the galaxies really are that early and really are that developed, the next question becomes unavoidable and a little uncomfortable. How sure are we? Really? How much of this rests on solid confirmation, and how much rests on first impressions that later softened under a harder, more skeptical look? Because the very first wave of impossible galaxies came with a warning attached, and that warning is part of the honest story too. Skipping that warning would make the whole account dishonest, and a dishonest version of this story would not survive its first real contact with better data. So before celebrating the most extreme claims, it is worth seeing which of them actually held up. The first wave of impossibly massive galaxies came with a caution attached to it, a warning that the louder retellings tend to forget entirely, and ignoring that caution would make this whole story dishonest. Real science includes the part where the first dramatic numbers get checked, and sometimes shrink. In the telescope's early days, one particular set of results landed especially hard. A team reported a handful of galaxies in the young universe that appeared not just bright, but enormously massive, holding so many stars so early that, taken at face value, they were extremely difficult to reconcile with any standard model. The numbers, if they were correct, suggested galaxies as substantial as our own Milky Way, already fully in place when the universe was only a small fraction of its current age. That would have been a genuine earthquake under the foundations of cosmology. It was reported, understandably, as one, and the phrase universe-breaking attached itself to the result almost immediately. But those first masses came mostly from the fast method, the one built on brightness measured through a set of filters rather than on a full spectrum, and mass is a famously slippery thing to read from brightness alone. To turn a galaxy's light into a count of stars, you have to make several assumptions, and each one carries uncertainty. You have to assume how the stars are distributed across different ages and sizes. You have to assume how much dust is dimming and reddening the view. You even have to assume whether some of the glow is coming not from stars at all, but from a feeding black hole at the galaxy's center. Change those assumptions, all of them defensible, and the estimated mass can swing dramatically. A galaxy that looks impossibly heavy under one reasonable set of choices can look merely surprising under another. That is more or less exactly what happened to several of those early headline galaxies. As more data came in, as spectra were finally taken, as the analysis was redone with different and often more careful assumptions, some of the most extreme mass estimates came down not to zero, not into the ordinary, but far enough that the word impossible no longer fit them honestly. What had first looked like galaxies too massive for the universe to contain settled, on closer inspection, into galaxies that were still remarkable, still surprisingly early, still a real puzzle, but no longer a flat contradiction of physics. Part of the mirage dissolved under a steadier, more patient look, the way mirages tend to. One particular reinterpretation deserves a closer look, because it did two things at once. For some of those apparently overweight galaxies, follow-up data suggested that a chunk of their light was not coming from a vast crowd of stars at all, but from a black hole feeding at the center, glowing fiercely as it swallowed gas. That single change in interpretation pulled the estimated stellar masses down, because you no longer needed billions of stars to explain the brightness. And at the same time, it quietly opened a brand new door. If black holes were already shining brightly inside galaxies this early, then black holes themselves were growing faster and sooner than the old picture allowed, which is its own kind of surprise. So the correction was not a simple retreat from one strange claim to nothing. It was a trade, swapping one puzzle for a different and arguably deeper one. And that pattern, of a problem changing shape rather than vanishing, is something we will see again before this story is done. It would be easy to take that as the deflating twist, the moment where the whole mystery turns out to be a simple measurement error and we all quietly go home. That is not the lesson, and pretending it is would be its own kind of dishonesty, just pointed in the opposite direction. Here is the more careful reading, the one that actually fits the evidence. Some specific, extreme claims softened when better data arrived. That is science doing precisely the thing it is supposed to do, correcting its first excited guesses with harder evidence. But the broad underlying pattern did not soften with them. Even after the most dramatic individual masses were revised downward, the early universe was still producing far more bright galaxies, far earlier than the models had ever predicted. This is the crucial difference between a single shocking object and a stubborn, repeating trend, and it is the hinge the entire story turns on. If the whole surprise had rested on just a few galaxies whose masses were overestimated, the problem would have quietly closed. The headlines would have faded, and you would never have heard the phrase, "too old" to exist at all. Instead, as the shakiest claims were filtered out one by one, what remained behind was not nothing. What remained was a steady, repeating excess of bright early galaxies that survived every correction thrown at it. The noise got cleaned up, carefully and honestly, and the signal was still sitting there underneath the noise, unmoved. So the honest position has to hold two things at the same time, and resist the temptation to collapse into either comfortable extreme. First, be genuinely skeptical of any single jaw-dropping object, especially before its distance and its nature have been confirmed by a full spectrum, because first impressions in this field have a real history of shrinking under scrutiny. Second, take the overall pattern seriously. because that pattern has refused to shrink no matter how hard it has been pushed. The individual galaxies that grab the headlines may rise and fall as the analysis improves. The trend they belong to has only grown more solid with every passing year of data. And once you hold both of those truths together, the story stops being about whether one particular smudge is real and becomes about something much harder to dismiss. Forget, for a moment, the arguments over exactly how massive any single galaxy is. Just look at what you are actually seeing when you look at that light, and at what it genuinely costs you to be able to see it at all. Because before we ask why the early universe is too bright, it is worth sitting quietly with the plain, strange fact of what these images even are. They are not pictures of the present. They are messages from the long dead, and that alone changes how the whole question feels. Before we argue about why these galaxies are too bright, we have to reckon with the stranger fact of what we are even looking at, and with the unforgiving limit that lets us see it only this once. Set the models aside for a moment, and just look at what you are actually holding when you look at one of these images. Because the object itself, stripped of any argument about it, is stranger than the dispute that surrounds it. That faint red point of light is not a galaxy. It is the light from a galaxy. And those two things are not the same. The galaxy that emitted it has spent more than 13 billion years doing whatever galaxies do over 13 billion years. It has formed and lost generations of stars. It may have collided with neighbours and grown into something far larger and more complex. It may have been torn apart and folded into a bigger structure that bears no resemblance to its young self. By now, in the actual present moment of the universe, it almost certainly looks nothing at all like the image we hold. The image is not a portrait of a thing that exists. It is a fossil, made of light, of a thing as it was in its infancy. An infancy that ended before the Earth had even begun to form. This is the part that does not fit comfortably in the mind. And it is worth deliberately letting it not fit, rather than smoothing it over. When you look at a photograph of a person who died long ago, you understand that the photograph is a record and not the person. The galaxy image is that same idea, taken to an extreme so vast it stops feeling like a number and starts feeling like a kind of vertigo. We are looking at one specific instant that ended an almost unimaginable span of time ago. And we are looking at it not because it was saved or remembered or preserved by anyone, but only because the light has been in transit this entire time and is just now, after the longest journey imaginable, falling onto a cold mirror in the dark beyond the moon. There is no other way to see it, and that is the limit that does not negotiate. We cannot wait for the light to update with newer news. We cannot ask the galaxy how it eventually turned out. Whatever it became, the news of it has not had time to reach us, and never will within any human timescale, because the distance only grows as space keeps expanding between us. We are permanently locked to this one ancient frame of it. The galaxy as it is now is, for us, simply unreachable, not hidden behind some obstacle we could move aside, but separated from us by an amount of expanding space and elapsed time that no signal we know how to send could ever hope to cross in return. Hold that, and the brightness problem changes its emotional weight entirely. It is one thing to read, abstractly, that a galaxy is more luminous than a model predicted. It is another thing to realize that this excess brightness is the only thing reaching across 13 billion years to tell us anything at all about it. These early galaxies are loud, in exactly the way that lets us hear them across the gulf. And we are straining at the very edge of what light can deliver. The faintness compounds with distance in a punishing way, because brightness falls off with the square of distance, so the furthest objects are dramatically dimmer for their true power. Push only a little further out, a little earlier, and even Webb's enormous, frozen infrared eye begins to lose the signal in the noise. We are not reading the early universe comfortably from an armchair. We are reading the last legible lines on a page before the writing fades into the dark. It is hard to overstate how faint these signals really are by the time they arrive. The light from one of these earliest galaxies has spread out across 13 billion years of expanding space, thinning the whole way, so that what finally lands on Webb's mirror is the barest trickle of photons, collected drop by drop over many hours of staring at a single point. The telescope does not so much photograph these galaxies as slowly accumulate them, the way you might fill a cup one raindrop at a time. And there is a deeper asymmetry hidden in that faintness, one that sharpens the unease. The relationship runs only one way. Their light can reach us, but nothing of ours can ever reach them. Not light, not signal, not influence of any kind. We can witness these galaxies, but we are utterly cut off from them, separated by an expanse that grows wider every second. We are spectators of a moment we can never touch, study a past we can never visit, and watch a beginning that finished its work long before there was anyone here to watch. And this is where a quiet dread enters the story, the kind that does not come from monsters or doom or anything invented to frighten you, but from sheer scale and sheer finality. The galaxies that are too early are also, every single one of them, gone in any sense that could ever matter to us. We are studying births that are, from our standpoint, also ancient deaths. We are arguing in detail about the youth of objects whose entire long lives have already played out, completely, beyond any possibility of our reach or our knowledge. The mystery of why they are so bright sits on top of a stranger and heavier fact. The only version of them we will ever possess is this one, this single, frozen, early instant, preserved by nothing but distance and time. And we get to read it exactly once. None of this makes the science less rigorous. If anything, it raises the stakes of getting the reading right, because we genuinely get only one look. There is no second exposure of the early universe waiting to be taken from a better angle next year. No way to circle around and photograph it again from the other side. There is only this light, arriving now, and our single chance to read it correctly, before it, and we, move on forever. Which is exactly why the pattern matters so much, and why the next realization is the one that turned a loose collection of strange individual objects into a problem the entire field suddenly had to face together. Because if it were only one galaxy, even a fossil this strange and this final, you could call it a curiosity and move on with your day. It is not one galaxy. It was never going to be that simple. If it were a single early galaxy, even a perfectly confirmed and perfectly strange one, it would be a wonderful curiosity and almost nothing more. One object can be a fluke. One object can be the rare exception that slipped through at the very edge of what physics narrowly allows. The whole reason this story carries real weight, the reason it stopped being a fun headline and became a genuine problem, is that Webb did not find one. It found a crowd where every model had promised a nearly empty room. This is the turn that changed everything, and it is worth slowing right down for. because it is the actual reason the calm of the field broke. Early on, the surprises could be argued about politely, one at a time. This galaxy might be a misidentified nearer object wearing dusty colours. That one might simply have an overestimated mass. The other might be a statistical accident, the kind you expect to find once if you look at enough sky. But as Webb kept looking, and as the surveys grew from a handful of deep individual pointings into wide systematic sweeps across larger and larger areas of the sky, the surprises stopped behaving like a list of individuals you could explain away. They started behaving like a population you had no choice but to account for. Large surveys are the key phrase here because they change the entire kind of claim you are able to make. A single deep image tells you only what happens to exist in one tiny patch of sky, and a tiny patch can always be unlucky or unusual. A wide survey, stitched together across a much larger area and analysed as a statistical whole, tells you something far more powerful. It tells you how common a thing actually is. One enormous Webb survey of this kind mapped an area of sky around 10 times the size of the full moon and catalogued on the order of hundreds of thousands of galaxies across cosmic time, building something close to a true census of the deep universe rather than a lucky snapshot. And when astronomers used surveys like that to measure how common these bright early galaxies really are, the number came back wrong, in a way that no single object could ever explain. The early universe was producing these luminous galaxies at a rate far above what the standard models predicted, not by a small, forgivable margin, by a large factor. In the most striking results, bright galaxies at these earliest epochs were turning up something like 100 times more often than the pre-Webb consensus models said they should, with the uncertainty still leaving the excess enormous, even at its most conservative edge. And it was not only the sheer number that surprised people, it was the shapes and the structures showing up far too soon as well. In the early universe, where the models expected only ragged, formless clumps still learning how to be galaxies, Webb has spotted objects with startling organisation, including a large, well-formed spiral disk, seen so early that its existence is genuinely hard to explain, since spiral structure was thought to take billions of years to settle into place. Surveys have turned up hundreds of bright candidate galaxies in the deep early universe, where a far smaller handful was expected, alongside whole populations of those puzzling little red dots. Each of these is a slightly different kind of surprise: structure, number, brightness, colour. But they all point in the same direction. The early universe was not the quiet, sparse, unformed place the models described. It was busier, more organised, and more luminous, on more fronts than anyone predicted. Sit for a moment with what that actually means. The models were not just caught off guard by one freak galaxy. They were systematically, badly underestimating how much bright material the early universe was assembling. You can lose an argument about a single galaxy's mass and walk away unbothered. You cannot wave away an entire population that is showing up far too often in survey after independent survey, in confirmed object after confirmed object. The excess is not a rumour whispered at the noisy edge of the data. It is a measured, repeated property of the early universe, robust enough that the very people who built the models are the ones reporting it against their own predictions. And this is also, finally, where the false older-than-the-universe framing falls completely apart and the real problem stands clear in its place. A single impossible object invites the fantasy that maybe the whole framework is secretly wrong. A population that is simply more abundant than predicted invites a sharper, more grounded, and far more answerable question. What specific assumption inside our model of early galaxy formation is making us undercount so badly. The framework of cosmology is not collapsing. A number inside it is off, and the size of that error is large enough that it cannot be ignored, cannot be shrugged away, and cannot be patched with a small, polite correction. The dread here is different from the fossil-light dread of a moment ago, and it is worth naming the difference precisely so they do not blur together. That earlier unease came from looking at one object and feeling the sheer weight of its distance and its finality. This new unease comes from repetition. It is the specific, creeping discomfort of finding the same anomaly everywhere you turn to look. One strange reading can comfortably be a glitch. The same strange reading over and over. Across independent measurements made by different teams with different instruments is not a glitch. It is the universe insisting on something. And insisting is exactly what nature does when a theory has quietly missed a real piece of how things work. The pattern does not let you comfort yourself with the word outlier, because there are simply far too many of them for that word to mean anything. So the mystery has quietly deepened past its opening shape, and it is worth tracking how far it has travelled. It started as, here is a surprisingly grown-up galaxy. It became, here is a confirmed early galaxy that is genuinely too developed for its time. And now it has become, the early universe as a whole is brighter and more productive than our model allows, and the size of the discrepancy is large. That is a far heavier claim, and it is the one the field actually has to answer. And just as astronomers were settling uneasily into that larger problem, the frontier moved again, further out than ever before, to a single galaxy so distant and so clear that it became the sharpest version yet of the entire puzzle. And then, in a wide-field survey of one well-studied stretch of sky, the frontier of the most distant known galaxy moved one more time, to an object that pushed the record further than anything before it, and made the whole problem genuinely impossible to look away from. The galaxy carries the designation MOM-Z14, and that name hides a small joke and a real method inside it. It came out of a survey built specifically to test these two early galaxies, a survey whose name plays directly on the question hanging over the entire field. Mirage or miracle? Were these astonishingly distant galaxies illusions after all? Tricks of dust and chance fooling the fast photometric measurements into reading nearby objects as ancient ones? Or were they real? And genuinely as extraordinary as they looked? MOM-Z14 was precisely the kind of answer that survey was hunting for, and the answer it gave was not the comforting one. Its redshift is about 14.5. In plain terms, its light has been stretched to more than 15 times its original wavelength, and it left its source when the universe was roughly 280 million years old. That is about 2% of the cosmos's current age, pressing the observable frontier right up against the dawn of galaxies themselves. At the time of its confirmation, it stood as the most distant galaxy ever confirmed, which means it is the earliest moment of a real, individual galaxy that human instruments have ever managed to read. And crucially, that distance is not a fast estimate that might evaporate. It was confirmed with a full spectrum, with the sharp hydrogen cliff in the light sitting exactly where a galaxy this far away should put it, backed up by the detection of several faint emission lines from the galaxy itself. There is very little wiggle room left in it. The galaxy is as early as it appears to be. That milestone alone would be worth a headline. The reason it sharpened the mystery rather than merely extending it is everything else about the object beyond its distance. MOM-Z14 is not a faint, struggling little knot of first light, the kind of timid, dim beginning the models would happily accept at that early epoch. It is luminous, far brighter than the standard picture says a galaxy has any business being so soon after the beginning. It is extraordinarily compact, packing its light into a region only a couple of hundred light-years across, tiny by the standards of a galaxy. It appears to be largely free of obscuring dust and, most pointedly of all, the analysis of its light suggests it is already chemically enriched, carrying the signatures of heavier elements that should only exist after stars have lived and died and seeded their surroundings. Brighter, denser, and more chemically mature than astronomers expected for something seen this early in cosmic history. Walk through why each of those is its own small problem. Because stacked together, they become the whole puzzle in miniature. Brightness this early implies a great deal of star formation packed into very little time. Chemical enrichment this early implies that an entire generation of stars has already been born, burned through its short life, and died, scattering the elements it forged, all within the first couple 100 million years of the universe. And compactness implies that all of this is concentrated tightly, not loosely and thinly spread the way the very earliest material was supposed to be. None of these is strictly impossible on its own. Together, in a single confirmed galaxy at the absolute edge of what we can see, they read like a checklist of exactly the things that were supposed to take longer than the time available. This is the entire puzzle compressed down into one object. And that is precisely what makes MOM-Z14 so important to the story. Everything that was diffuse and arguable about the broader population, the brightness excess, the early maturity, the unshakable impression of a universe moving faster than the clock should allow, is here concentrated into a single, confirmed, record-breaking point of light. You cannot dismiss it as a misread near a galaxy, because the spectrum settles the distance beyond reasonable doubt. You cannot dismiss it as one overestimated mass lost in a noisy crowd, because it is a clean, individual confirmation standing on its own. It is the mystery with all of the usual excuses, already removed in advance. Remember the question baked into that survey's name? Mirage or miracle? And notice what this object does to it. A mirage would have been the comforting answer. A nearer, dustier galaxy, masquerading as an ancient one, easily explained once the spectrum exposed the trick. MOM-Z14 refused to be that. The spectrum confirmed it was exactly as distant and as early as it looked. And yet, it was still bright, compact, and chemically enriched. The survey asked whether these galaxies were illusions or genuine wonders, and this object answered firmly on the side of the wonder. Sit with what its enrichment really demands in terms of time. For heavier elements to be present this early, an entire generation of stars had to form, burn through their fuel, and die, scattering the elements they forged into the surrounding gas, all within the universe's first few 100 million years. That is a complete stellar life cycle, beginning to end, compressed into a sliver of time we once assumed was barely enough for the first stars to even ignite. The clock did not stretch. The cosmos simply did more inside it than we believed it could. It is worth marking how far the frontier has travelled to get here, because the speed of that movement is itself part of the surprise. Only a few years ago, before Webb began its work, the most distant galaxy known had been found by Hubble and sat alone as a single confirmed point in the universe's first 500 million years. Today, that once record-breaking galaxy is no longer even in the top 10 most distant. It has been passed by more than a dozen others, with a galaxy at a redshift of around 14 1/3, confirmed shortly before MOM-Z14 took the lead. The record is not just being broken, it is being broken repeatedly, quickly, and each new holder tends to be brighter and stranger than the last. And the researchers behind the latest record did not soften the implication or hide behind cautious vagueness. Their own framing was blunt and honest. There is a widening gap, they noted, between what theory predicts for the early universe and what the telescope keeps actually showing. Not a broken universe, not a disproven Big Bang. A growing distance between prediction and observation, stated plainly by the people best positioned in the world to judge it. That is the sound of a healthy field openly admitting that its model has missed something real, and then going looking for the missing piece in good faith, rather than pretending it was never lost. Which raises the obvious and final question, the one that actually matters more than any record. If the universe is not broken, and the galaxies are real, and they truly did grow this fast, then what is the missing piece? What could possibly let the early cosmos build bright, enriched, substantial galaxies far faster than we thought possible, without tearing up the laws of physics to do it? Because the most important part of this entire story is not the shock of the discovery. It is that there are real, grounded, testable answers already on the table, and not one of them requires the universe to be a lie. None of this requires the universe to be broken, and that is the part the headlines almost never reach, because it is harder to shout. There is a whole menu of explanations on the table, every one of them grounded in physics we already understand, and the real scientific work happening right now is figuring out which of them, or which combination of them, is doing the heavy lifting in the early universe. Start with the most down-to-earth possibility, the one that is almost boring and may well be partly true anyway. When you survey a huge area of sky and pick out the brightest objects in it, you are unavoidably biased towards catching things at the very peak of their brightness. And star formation in early galaxies may well have come in intense, dramatic bursts rather than as a steady, even glow. A galaxy that flares brilliantly for a relatively short while, as a great wave of new stars ignites all at once, is far easier to spot than the very same galaxy in one of its quiet, dim phases. So the early universe might actually be making roughly the number of galaxies expected overall, but we are preferentially catching them mid-flash, which makes the whole population look brighter and more abundant than it truly is on average. Part of the excess could simply be the universe blinking, and us holding the shutter open at exactly the bright moments. Next, consider what the very first stars were actually like, because they were not like the stars around us. Today's star formation produces a familiar mix, with many small, dim, long-lived stars for every rare giant. But the first stars formed from almost pure hydrogen and helium, with none of the heavier elements that change how a cloud of gas cools and collapses. That different starting chemistry may have favoured a very different mix of stars, tilted strongly toward more massive, hotter, more luminous ones. A galaxy that builds a larger share of heavy, brilliant stars will shine far more brightly for the same total amount of material. If the early universe was routinely making these top-heavy populations, then too bright for its mass quietly stops being a paradox at all. The light is high, but the underlying mass need not be anywhere near as extreme as the brightness first suggested. We may simply have been converting that light into mass using the wrong recipe. There is a closely related idea about efficiency, and it may be the most important of all. In the present-day universe, galaxies are surprisingly bad at turning their available gas into stars. Feedback constantly gets in the way. Exploding stars and the fierce winds and radiation from massive young stars blow gas outward and heat it up, slowing or shutting down further star formation, so that only a modest fraction of the raw material a galaxy holds ever actually becomes stars. But conditions in the dense, compact, deeply gravity-bound early universe may have been genuinely different. If early galaxies were simply much more efficient, converting a far larger share of their gas into stars before feedback had time to choke the process off, they could grow bright and substantial far faster than models tuned to the modern, wasteful universe would ever predict. Same physics, different setting, dramatically different result. Then there are the black holes. And this may be the most intriguing thread of all. A growing suspicion among astronomers is that some of these bright early objects are not shining purely with starlight at all. When a black hole feeds on the gas swirling around it, that gas heats to enormous temperatures and blazes with light, and that glow can easily outshine all the stars around it. A small, dense, early galaxy with a hungry black hole at its heart could look far more luminous and far more developed than its actual stellar population alone would suggest. This connects directly to one of Webb's other strange early universe discoveries: a population of small, intensely red objects, nicknamed little red dots, that appear to harbour far more vigorous central activity than anyone expected, hinting that black holes grew up alongside their galaxies faster and earlier than the old picture ever allowed for. It is worth lingering on why the early universe might have been so much more efficient, because the mechanism is concrete rather than hand-waved. In a normal galaxy, star formation is partly self-limiting. The first massive stars to form quickly flood their surroundings with radiation and then explode, and those explosions and winds heat and blow away the very gas that would have made the next stars, throttling the whole process. But in the dense, compact early galaxies, gravity was strong and the gas was packed tightly, so a great deal of star formation could happen before that destructive feedback had time to switch on and clear the room. The galaxy got a head start, building stars furiously in the window before its own newborn stars learned to push back. Crucially, none of these four explanations rules out the others, and the likeliest truth is that several of them operate together, in proportions that differ from galaxy to galaxy. A given bright early object might owe some of its glow to a burst caught at its peak, some to an unusually top-heavy crop of brilliant stars, some to ferocious early efficiency, and some to a feeding black hole at its core. Untangling those contributions, one object at a time, is exactly the slow work the field is now engaged in. Now notice the shared shape of all four of these explanations. Because the shape is the reassuring part. Bursty star formation catching us at peak brightness. A top-heavy mix of brilliant first stars. Higher efficiency in turning gas into stars. Extra light from feeding black holes layered on top. Not one of them rewrites gravity, or the expansion of space, or the basic timeline of the Big Bang. Each of them is a tweak to the messy, complicated, genuinely uncertain business of how gas becomes light in the first few 100 million years. That part of the story was always the least settled, the part built on assumptions extrapolated downward from a universe we knew much better. The grand framework of cosmology stands untouched. It is our detailed recipe for cooking up early galaxies that needs adjusting. And these are simply the ingredients we are now arguing over. But there is one more category of explanation that has to be put on the table honestly, and it is the one that makes the whole field sit up a little straighter, because it does not just tweak the recipe in the kitchen. It asks whether the kitchen itself, the underlying cosmology, the very rules governing how fast structure was allowed to grow might need a small but genuine change. And that question is where the real, unresolved, still open tension finally lives. The one that has not been settled and may not be settled for years to come. Which leaves the largest question standing alone, the one all the others were quietly circling. What if the problem is not only in how we model gas and stars and black holes, but somewhere deeper in the underlying machinery of the universe itself, in how fast structure was ever allowed to grow at all? To see why any serious scientist would even raise such a possibility, you have to understand what the standard model of cosmology is actually doing in the background of all this. It is not mainly a theory of galaxies. It is a theory of how matter, both the ordinary kind and the invisible dark kind, gathered itself into structure over cosmic time. It starts from the almost perfectly smooth early universe, just after the Big Bang, and describes how tiny variations in density slowly clumped together under their own gravity over hundreds of millions of years into the vast cosmic web of galaxies and clusters we see today. That growth has a definite pace, set by the ingredients of the universe and the rules those ingredients follow. And here is the constraint that makes the early galaxies so provocative. Galaxies can only assemble as fast as gravity can pull their raw material together. If far too many big, bright galaxies appear far too early. One possible reading is that structure itself grew faster than the standard pace should ever allow. If that reading were correct, the fix would not be a better recipe for star formation. It would be a change to the cosmic ingredients or the cosmic rules themselves. Something that lets matter clump together earlier and more vigorously than the standard model predicts. Researchers have floated several such ideas, and it is essential to be clear that all of them sit firmly in the realm of speculation, clearly labelled as such by the very people proposing them. A different behaviour of dark energy in the early universe, sometimes called early dark energy, that would speed up structure formation in the first moments. More exotic forms of dark matter than the standard cold kind, or small changes to the initial conditions left over from the very beginning. The precise pattern of those first tiny density ripples. Each is a way of speeding up early structure formation without throwing physics out entirely. And each, honestly, comes at a real cost. These adjustments tend to require extra ingredients, extra free parameters, extra fine-tuning, and they risk breaking other things that the standard model currently gets exactly right. That last point is the crucial one, and it is where the field's caution reveals itself as a strength rather than a weakness or a cover-up. The standard model is not fragile or arbitrary or propped up by stubbornness. It is held firmly in place by many completely independent measurements that all agree with one another to remarkable precision. The faint afterglow of the Big Bang, the oldest light in the universe, encodes the early conditions in exquisite detail. The way galaxies are distributed in great patterns across the whole sky traces the growth of structure. The abundances of the lightest elements match predictions from the first few minutes of the universe. You cannot reach into this tightly woven model and simply speed up early galaxy growth without risking damage to all those other hard-won agreements. They are connected, and pulling one thread tugs on the rest. And when researchers actually checked, the constraints came back strict, using older, wide surveys from before Webb that placed tight limits on how many galaxies there can be in the early universe. Careful analyses argued that the standard model still fits that earlier data very well. The argument from those urging caution is direct and worth stating fairly. If cosmology were truly broken at its foundation, we would expect the damage to show up not just in Webb's narrow view of the brightest early galaxies, but across many other datasets too, in the afterglow of the Big Bang, and in the broad distribution of galaxies. And largely, they argue, it does not. The trouble seems concentrated in this one specific corner, the brightness and abundance of the earliest galaxies, rather than spread destructively across everything we measure. A foundation that was genuinely cracked would, they point out, leave cracks in more than one wall. So the field is split, and the split is honest and out in the open rather than hidden. On one side are researchers who argue that the standard model is almost certainly fine, that the surprises live entirely within the messy, poorly understood astrophysics of early stars and gas and black holes, and that better recipes for star formation will eventually absorb the whole anomaly without any need for new cosmology. On the other side are those who note, correctly, that the gap between prediction and observation has not actually closed, that it has, in some respects, widened as the data has improved, and who think it is at the very least worth taking seriously that something deeper might be contributing. Neither side is being foolish or dishonest. Both are looking at the same growing tension and weighing the same evidence differently, which is exactly what scientists are supposed to do at the edge of knowledge. This is the genuine, unresolved heart of the whole story, and it is far more interesting than any false certainty pointed in either direction would be. The most likely outcome, by the careful judgment of most of the people who actually work on this, is that the answer lies almost entirely in the astrophysics, bursts, and efficient star formation, and top-heavy early stars, and feeding black holes, combining together to make the early universe genuinely brighter than our old models guessed, with no new cosmology required at all. That is the boring, probable, and frankly rather elegant resolution, and it is where the smart money sits. But most likely is not the same as certain, and the people closest to the data are careful to keep the deeper door from being slammed shut prematurely, because the chasm between what theory predicts and what Webb actually shows has not yet been talked away. That uncertainty is not a failure of science. It is the exact state a healthy science is supposed to be in when it runs headfirst into something real and new and unexpected. There is a measured anomaly that will not go away. There are several grounded, physics-based explanations competing to account for it. There is genuine, open disagreement about which is right, conducted respectfully in journals rather than shouted in press releases. And there is a clear path forward. Because the one thing everyone in the argument agrees on is what would actually settle it. More data, of a few specific kinds, aimed precisely at the weak points of each explanation. The question is not whether we can find out. It is what, exactly, we still need to go and see. The honest position is that this is not finished, and the most respectable thing the field can say about it right now is also, fittingly, the least dramatic. We do not yet know which explanation is correct, and here is precisely what would tell us. Measurement by measurement. The single most powerful tool is the very one that already turned the first frightening candidates from rumour into hard fact. Spectroscopy, applied patiently to more and more of these objects, every single time a galaxy's distance is confirmed with a full spectrum rather than merely estimated from its brightness, the population of genuinely early galaxies gets more solid and a little less arguable. The early surprises were vulnerable to doubt precisely because so many of them rested on fast photometric estimates that could be fooled. The cure is unglamorous, patient confirmation, one careful spectrum at a time, until the sample of truly confirmed early galaxies is large enough that no one can wave the trend away as a pile of misreadings and dusty imposters. That work is ongoing right now, and it is slow. And it is exactly what a careful field does when it suspects its own first impressions ran out ahead of its proof. But spectra do far more than pin down distance, and this is where the next real answers will come from. A detailed spectrum can reveal what a galaxy is actually made of, how enriched it truly is with heavy elements, and, most importantly for this puzzle, whether its light is dominated by stars or by a feeding black hole at its center. That last distinction is enormous, because it directly tests one of the leading explanations. If the brightest early galaxies turn out to be powered substantially by black holes rather than by starlight, then much of the too much, too soon problem softens immediately, because it would mean we have simply been over-counting stars where the light was really coming from gas falling into a black hole. If, instead, the light proves to be clearly and dominantly stellar, the problem stays sharp and the pressure on our star formation models grows heavier. The spectrum is the witness that can tell stars and black holes apart, and the field is now calling that witness, galaxy by galaxy, to testify. There is also the matter of the very first stars themselves, the pristine, metal-free generation that would have to be top-heavy and brilliant for one of the leading explanations to fully work. Astronomers call them population 3 stars, and despite years of searching, we have not yet cleanly seen a population of them. They are predicted, they are necessary to the story, and they remain frustratingly out of confirmed reach. Finding their unmistakable signature, the spectral fingerprint of stars made from pure hydrogen and helium, with essentially no heavier elements at all, would directly test whether the early universe really was building the kind of bright, massive stars that could explain the excess light. That search is one of the hardest things Webb has ever been asked to attempt, and a clear detection, or a confident absence, would move the entire argument substantially one way or the other. And Webb does not, and will not, work alone on this. A new generation of wide survey instruments is coming online that will map enormous swathes of the sky far faster than Webb's deep, narrow stares ever could. These survey telescopes, both on the ground and in space, will turn the question of abundance from a series of small, hard-won samples into a true statistical census of the early universe. Remember that the brightness excess problem is, at its core, a counting problem. How many bright galaxies are there, this early, compared to what the models allow? You answer a counting problem properly with a far bigger, far more complete count taken across a much larger volume of the early universe, so that statistical flukes and small sample surprises wash out, and the real underlying number finally stands clear and undeniable. Much of the next decade of cosmology is built around exactly this kind of large-scale mapping, and the early galaxy puzzle is one of the first things that flood of new data will sharpen. There is also a clever way to reach the galaxies that are normally too faint to see, and it matters because of a worry we raised earlier. If we only ever study the very brightest early galaxies, we risk being fooled, because the brightest objects are the easiest to spot and may not represent the typical ones. The fix is to use gravity itself as a lens. When a massive cluster of galaxies sits between us and the deep universe, its gravity bends and magnifies the light of objects behind it, acting as a natural telescope that boosts faint, ordinary early galaxies into view. By pointing Webb through these cosmic lenses, astronomers can sample not just the rare giants, but the more representative population beneath them, and check whether the brightness excess holds up once the fainter, more typical galaxies are counted too. It is a way of testing whether we have been dazzled by the outliers, or whether the whole early population really does run brighter than predicted. Notice carefully what this whole list is not. It is not a promise that the universe is secretly broken. And it is equally not a promise that everything is comfortably fine and the mystery is already solved. It is a concrete set of specific measurements, each one aimed at a specific fork in the argument. Each one genuinely capable of pushing the answer toward ordinary astrophysics or, less likely but not impossibly, toward something deeper in cosmology. That is what a real scientific frontier looks like from the inside. Not a finished verdict handed down from on high, but a set of questions made sharp enough to actually be answered, and a fleet of instruments being built and pointed precisely to answer them. It is worth being honest about the timescale too, because this is exactly where patience earns its place against the pull of the headline. These answers will not arrive all at once in a single dramatic press conference. They will accumulate slowly, spectrum by confirmed spectrum, survey by completed survey, paper by careful paper, over many years. The phrase, "too old to exist," can be typed and shared in a single second. The actual resolution of why the early universe burned so bright will take a long, careful, unhurried while, and it should, because we get exactly one look at this ancient light, and we owe it a correct reading far more than we owe anyone a fast one. So before we say what it all most likely means, it is worth gathering the pieces we are genuinely sure of, laying them out plainly in order, and seeing how cleanly they actually fit together once the noise is stripped away. So gather the pieces and lay them out carefully in order, because when you do, the real shape of this story turns out to be cleaner and stranger and far more durable than the headline ever managed to be. Start with what is genuinely solid, the ground that no longer shifts. The distances are real. The galaxies that have been confirmed with full spectra are truly as far away and therefore as early as they appear to be. That part is no longer in serious scientific doubt, and it is the bedrock that everything else in this story rests upon. When the light says a galaxy is from the universe's first few 100 million years, with that sharp hydrogen cliff sitting exactly where it should, the light is telling the plain truth. The record holders are real records, not mirages. Had the second solid piece just as firm as the first? These early galaxies are, taken on the whole and as a population, brighter and more abundant than the standard models ever predicted. And that excess is emphatically not the product of a single freak object that could be quietly corrected away. It survived the cleanup. When the most extreme early mass claims were carefully revised downward, it survived the move from a few lucky deep pointings to wide, systematic surveys covering large areas of sky. It survived the jump from fast photometric estimates to slow, hard, spectroscopic confirmations. Whatever else remains uncertain in this story, the early universe really did produce far more bright galaxies, far sooner than we ever expected. That is a measured fact about the cosmos, not a feeling, and not a fashion. Now place the third piece carefully, the one that corrects the myth and keeps us honest. None of this means anything is older than the universe, and none of it means cosmology itself is broken. The phrase, "too old to exist," describes a paradox that the measurements themselves directly rule out, because a galaxy's distance and its age are the same fact seen from two sides, and nothing can be older than the cosmos that formed it. What the evidence actually shows is a problem of pace and not of age. Galaxies that grew bright, dense, and chemically mature faster than our recipe for building them said was possible. The clock is fine. The construction schedule is the genuine surprise. Set the fourth piece down beside it, the one that turns the surprise from a wall into a workable question. There are several grounded, physics-based explanations for that fast construction, and not one of them requires rewriting the universe. Star formation may come in brilliant bursts that we keep catching at their absolute peak. The first stars may have been top-heavy and blazing, producing far more light for far less mass than later stars do. Early galaxies may have converted their gas into stars with unusual, ferocious efficiency before feedback could shut them down. And feeding black holes may be adding extra light that we have been mistakenly counting as stars. Most likely, several of these are acting together at once, and most researchers genuinely expect that this messy, ordinary, knowable astrophysics, and not any new cosmology, will absorb the anomaly in the end, and then lay down the last piece, the one that keeps the door honestly and deliberately open rather than forcing it shut. Most likely is not the same as certain, and good scientists refuse to pretend otherwise just because it would feel tidier. The gap between what theory predicts and what Webb keeps showing has not closed, and a thoughtful minority of careful researchers think it is at least worth seriously asking whether something deeper in the very growth of cosmic structure might be quietly contributing to it. That possibility is tightly constrained by other measurements. It is openly speculative, and it carries real costs in fine-tuning and broken agreements elsewhere. But it has not been firmly ruled out, and the people standing closest to the data refuse to pretend that it has. Put all 5 of those pieces together on the table, and the true story finally stands clear and whole. Webb did not find galaxies older than the universe. It found that the early universe was a far more productive, far brighter place than we had believed it could be, and in doing so, it caught our own model of cosmic dawn making a real, measurable mistake about how fast the first galaxies were able to grow. That is not a smaller story than the headline promised. It is a genuinely better one because it is real, and because it points somewhere specific and reachable rather than nowhere at all. The mystery is not a dead-end wall. It is a crack with light spilling through it, and the light is leading somewhere we can actually follow, step by careful step. If you want one image to carry away from all of this, make it this one. Picture the whole of cosmology as a great building. The foundation is the part that describes how the universe expanded and cooled, how matter gathered under gravity, how the cosmic web took shape, and that foundation has been tested from a dozen independent directions and is still standing without a visible crack. What Webb has called into question is not the foundation, but the blueprint for one particular room, the detailed plan for how gas turns into stars and galaxies in the first few 100 million years. That blueprint was always the most provisional part of the design, sketched from assumptions extrapolated downward from a universe we knew far better. Finding that this one blueprint is wrong does not bring the building down. It tells us we drew that one room incorrectly and sends us back to redraw it with better information. That is a very different thing from the headline's claim that the whole structure is collapsing. And it is the distinction that separates a working science from a sensational story about one. This is the verdict the evidence currently supports, and it is a verdict that deliberately leaves work undone, which is exactly as it should be. The early galaxies are confirmed. The brightness excess is real and robust. The age paradox is a myth that the measurements themselves dissolve. The explanations are grounded and testable and competing, and the deepest question of all is still genuinely open. That is precisely the state of knowledge you would expect to find at a real frontier, and it is far more honest and far more interesting than any false certainty pointed in either direction. But there is one more thing these images quietly carry, beyond the galaxies and beyond the argument, and it is the quietest and the heaviest part of the whole story. Because there is a place in every one of these deep pictures where the galaxies, simply stop. There is a place in every one of Webb's deepest images where the galaxies simply stop appearing. And that edge is the real horizon of this entire story, the limit that no better telescope and no future genius can ever argue its way past. Push outward through the data, to higher and higher redshift, to earlier and earlier times, and the galaxies thin out, and then they run out completely. Not because the universe ends there, but because you have reached back to a time before the first galaxies had finished forming at all. Beyond the earliest galaxies lies an era astronomers call the Cosmic Dark Age, a long stretch after the universe cooled out of its hot, dense beginning, but before stars had yet switched on to light it from within. In that age, there were no galaxies to find, because there was nothing yet shining to be found. The room is not empty because we lack the technology to see into it. The room is empty because, for a genuine stretch of cosmic time, there was simply no light in it to see. And past even that dark age, further back still, there is a true and final wall. Go back far enough and the universe was so hot and so dense that it was not transparent at all. Light could not travel freely through it. It scattered endlessly off the dense fog of charged particles, the way light scatters and gets lost inside thick fog on Earth, unable to carry an image anywhere. Only when the universe had expanded and cooled enough did it suddenly become clear, in an event astronomers call recombination, releasing the light that we still detect today as a faint, even glow filling the entire sky in every direction. That glow is the oldest light in existence, the afterglow of the beginning itself, and it marks the furthest back that any light can ever take us. Behind it, there is no image to recover, no fainter red dot waiting patiently at higher redshift for a bigger telescope, because before that moment, light simply could not get out at all. It is not a wall we lack the cleverness or the funding to cross. It is a wall built into the fundamental nature of light and the early universe itself. There is one faint, difficult hope of glimpsing into the dark age that lies between the last galaxies and that final wall, and it is worth mentioning precisely because of what it cannot do. Even when there were no stars shining, the universe was full of cold hydrogen gas, and that gas quietly emits a particular radio signal. In principle, by listening for that whisper rather than looking for starlight, future radio observatories might one day map the dark age itself, the era before the first stars switched on. It is an enormously hard measurement, still in its earliest attempts, and it would peer into the darkness in a completely different way than any telescope chasing galaxies. But even this technique stops at the same place. It can probe the dark age, but it cannot reach back past recombination, past that wall of last scattered light, because before then, there was nothing transparent for any signal to cross. However we approach it, looking or listening, the universe keeps the same final door closed. This is the deepest limitation in the entire story, and it is worth feeling its exact shape, because it is nothing like the ordinary frustration of merely needing a bigger machine. Most limits in astronomy are practical and temporary. Build a larger mirror, fly to a darker and colder place, wait for a longer exposure, and you see further than before. This limit is categorically different. It is fixed by physics, not by engineering or budget or patience. We could build a telescope 100 times more powerful than Webb, 1,000 times more powerful, and we would still slam into the same wall at the same place. Because the obstacle is not faintness that more light gathering could overcome. The obstacle is that there was no free light to emit in the first place. The galaxies that get called too old to exist sit just inside that final lit region, almost the very first things there ever were to see, pressed right up against the edge of the visible past, with nothing observable behind them. That is what gives this whole search its quiet, particular weight. When astronomers chase ever higher redshifts, breaking record after record, they are not simply collecting trophies. They are walking, deliberately, toward a boundary they can never actually step over, gathering up the last legible galaxies before the light gives out entirely. Each new record holder is one more step closer to a frontier that is genuinely, permanently final. There is a most distant galaxy that we will ever be able to see. Somewhere out there in that thinning crowd near the edge of the Dark Age, and once we reach it, there is no further left. Not for Webb, not for any instrument we could ever dream of building. Not ever. The page does not just slowly go dark. At some point, it ends. And here is where the strangeness of these particular galaxies and the strangeness of the wall finally meet and reinforce each other. The objects that are too bright and too early, the ones that broke our careful schedule for cosmic dawn, are the very objects living closest to that final edge of all visibility. They are our last clear messengers from the moment the universe first lit itself up out of the long darkness. So, if they are telling us, insistently, that the early cosmos grew faster and shone brighter than we ever thought, then they are reshaping our understanding of the one single chapter we can barely read at all and can never, ever go back and read more closely. We are learning that the beginning was busier than we imagined, and we are learning it from the faintest available light, at the absolute limit of what light itself can show us. There is something humbling in that, and something a little frightening. There is no rescue from this particular limit, no clever workaround quietly waiting to be invented in some future laboratory. And that is not really a tragedy so much as a hard fact to stand respectfully in front of. The universe will let us see almost all the way back to the first stars, an astonishing gift when you think about it. And then it closes the door. What we can ever know about cosmic dawn, we will have to learn from this one narrow band of ancient light, these last galaxies before the dark. Read as carefully and as honestly as we can possibly manage, which means every one of these too early galaxies matters more, not less, because they are not merely puzzles to be solved at our leisure. They are very nearly the last witnesses to the universe's first morning, and they will not speak to us twice. So in the end, the whole story comes back around to exactly where it started, to that single faint smudge of red light, and to what it is really asking of us, which returns us, finally, to that faint red smudge, the one your eye would have slid right past without a second thought, sitting quietly in a corner of one of Webb's deep images, as it has sat, unnoticed, for 13 billion years, until now. We can read it more honestly now, having walked the whole path to get here. It is not a galaxy older than the universe because nothing is or can be. It is not proof that physics is broken or that the Big Bang never happened, because the very same light that reveals it is the thing that rules those claims out. It is something far more careful and far more durable than any slogan. It is light from one of the first bright galaxies, sent across more than 13 billion years of expanding space, arriving on a frozen mirror now, today, to tell us that the early universe was further along than we ever believed it could possibly be. The smudge is not breaking the laws of nature. It is gently correcting our story about how quickly nature got itself started. And it is not alone. which is the entire reason it matters at all. If it were a single freak, a 1 in a trillion accident, you could file it away and reasonably forget it. Instead, it belongs to a growing, confirmed crowd of early galaxies, all of them whispering the same uncomfortable thing in slightly different voices. Too bright. Too soon. Too many. The most extreme individual claims among them have softened under scrutiny, exactly as good science demands they should, but the underlying pattern beneath the claims has only hardened with time. The early universe really did build bright, substantial, chemically enriched galaxies faster than our best recipe allowed, and the gap between what we confidently predicted and what we actually see is real enough, and stubborn enough, that the people who study it for a living are the very ones standing up to point at it. The likely answer, the one most researchers quietly lean toward when pressed, is reassuring in its ordinariness, and there is a kind of beauty in that. Bursts of star formation that we keep catching at their brightest moment, first stars tilted toward the massive and the luminous, early galaxies that turned their gas into stars with an efficiency the modern universe has forgotten how to manage, feeding black holes adding their own fierce light, which we have been miscounting as stars. Some blend of these, every part of it grounded entirely in physics we already trust and understand, most likely closing the gap in the years just ahead without any need to rewrite the cosmos at all. The deeper possibility that something in the very growth of structure itself was different in those first moments remains genuinely open but tightly constrained, kept honestly alive only by the people who refuse to pretend a real tension has already been resolved when it has not. That, in the end, is the part that stays with you, and it is worth saying it plainly one final time. The truly unsettling thing here is not a monster, or a doom, or a broken universe collapsing around us. It is something much quieter, and far harder to shake once you have felt it. It is the realization that our clearest picture of the beginning has a real, measurable error sitting inside it. An error discovered at the exact outer edge of what light can ever show us, in objects we are permitted to look at only once, and never, ever again. We are reading the first chapter of the universe from its last legible lines, and those lines do not say quite what we expected them to. We do not yet know why. We know how to find out, slowly, spectrum by spectrum, survey by survey. And we know there is a hard wall just beyond these galaxies where the looking itself finally has to stop, where even the most powerful instrument imaginable goes blind. It is worth feeling the difference between the two kinds of dread on offer here, because only one of them is real. The headline sells a cheap and thrilling version. The universe is broken. Everything you were taught is wrong. The experts have been exposed. That version is exciting for exactly as long as it takes to remember it is not true. The real unease is slower and stranger, and does not fade when you check it. It is the quiet vertigo of standing at the edge of the visible past and finding that our map of the beginning, drawn so carefully, has a genuine error right at its border, in a region we can study only once and never return to. There is no villain in that, and no apocalypse. There is only the universe, behaving exactly as physics demands, and turning out to have built its first galaxies faster than we guessed, in a place we can barely reach, and can never reach beyond. That is a harder feeling to hold than the headline, and a more honest one, and it does not need a single exaggeration to earn its weight. So the next time you see that phrase scroll past you, "Galaxies too old to exist," you will know exactly what it is really pointing at, underneath all the noise. Not a paradox, a pace. Not a broken universe, but a universe that simply grew up faster than we thought it could. Caught in the act by a telescope built specifically to see the colours that 13 billion years of cosmic expansion had hidden from every eye before it. The mystery is completely genuine. The dread, if you feel a little of it, is the honest kind, the kind that comes from sheer scale and sheer finality rather than from anything invented to frighten you. And the answer is not being hidden by anyone. It is just hard and far away and absolutely worth the patience it demands. If a question like this is the reason you came, the kind where the strangeness is real and the science is still being written in front of us, then stay with these stories, because the early universe is full of them, and Webb has only just begun. And before you go, leave a thought in the comments on the one piece that lands hardest for you. Is it the speed? The unsettling fact that the first galaxies grew up faster than all our models allowed? Or is it the wall? The fact that just beyond these last bright points, the light gives out completely and the looking ends forever. I read those, and that single question is exactly the edge the entire field is balanced on right now. The smudge is still there, in the data, faint and red and endlessly patient. It has waited 13 billion years to reach us. The very least we can do, in return, is read it correctly.